I got some questions about an article that recently appeared in New Scientist, according to which some physicists found a way to quash the idea of the multiverse. I was super impressed because I thought that was impossible. So of course I had a look. The reason I think it's impossible to quash or rule out or otherwise question the idea of a multiverse is that it's not a scientific theory. If there are universes other than our own, they're unobservable. We can't ever either confirm or falsify their existence. The New Scientist article is about a specific type of multiverse, that's the many worlds interpretation of quantum mechanics. This interpretation has it that every possible outcome of a quantum measurement happens in its own universe. Just so happens that we only ever observe one. New Scientist reports on a paper which claims to solve a problem in quantum mechanics that goes like this. Suppose you have one quantum of light, one photon, and you send that through a beam splitter. The photon is then in a superposition of left and right, let's say in equal parts. According to standard quantum mechanics, before you make a measurement, the photon is in both places at once. But if you measure it, then half of the time you find it left, half the time right. The problem is that this process must conserve momentum because it's a holy law of physics. Without it, the universe would quite literally fall apart. In the case of this photon, the momentum is just an arrow pointing into the direction that the photon travels. You see the problem now. The photon goes in that direction, but if you measure it here, it's going in that direction or that direction. Momentum can't be conserved. This shouldn't happen. The authors in the paper now claim that the standard way quantum mechanics deals with this problem is to say that what conservation laws mean is that if we repeat measurements on a statistical ensemble of identically prepared systems, we get the same statistical distribution. In other words, they think that in quantum mechanics, conservation laws are merely fulfilled on average in many repetitions rather than in every single measurement. They say in the paper that the issue does not occur at the level of the many worlds interpretation because if you take together all those many worlds, then each single run of the experiment is the average. You never have an issue with conservation laws in the entire multiverse, just apparently so in one universe. Their paper is then dedicated to solving this problem of conservation laws in only one universe. And this, they claim, removes the motivation for the many worlds theory. In New Scientist, the lead author is quoted as saying, "We've essentially demolished one of the arguments for it. This is nonsense. First, I've never heard anyone make this argument for the many worlds interpretation, so they're demolishing a straw man. But worse, the problem that they claim to solve doesn't exist. Conserved quantities are always conserved in total in every single run, in every experiment in quantum mechanics, not just on average. In the case of the beam splitter, this is because if the photon goes through the splitter, it strictly speaking doesn't just create a superposition of left and right. It creates a superposition of the photon with momentum going left and the beam splitter moving a tiny bit right, plus the photon going right. The momentum is conserved for each case separately because the beam splitter also moves. It's just that the motion of the beam splitter usually can't be measured, so we don't bother writing it down. We know that total conservation laws are fulfilled in each instance of an experiment because, strictly speaking, all interactions would have to be described by the standard model of particle physics, and that has conservation laws built in. If your quantum maths violates them, you did something wrong. How do they solve the problem in the paper? By inventing an additional carrier for the conserved quantities that they call the preparer. They introduced this so that the conservation law is fulfilled at each interaction. And that is right, but this is what always happens. By the way, this video comes with a quiz that lets you check how much you remember. Here is the interesting thing though. Quantum mechanics does have a problem with conservation laws. Let's look again at the beam splitter example. As I said, the total momentum is conserved, but it isn't locally conserved when you make a measurement. Because before the measurement, you have half the momentum of the photon there and half here. After that, it suddenly jumps to only one side. The total momentum is the same in both cases, but the change is non-local, and that isn't compatible with Einstein's theory of general relativity. The only way you can solve this problem is to violate measurement independence. That's what's sometimes called superdeterminism. It's provably, by Bell's theorem, the only way to fulfill local conservation laws in a measurement process. This is so obvious, and all I can do is repeat this, hoping that eventually one day they'll understand it. But if that day comes, we can then say that science progresses one YouTube video at a time and you made it happen, so don't forget to subscribe. Yes, I've been talking about quantum physics again. It's definitely my favorite topic. But did you know that I have a quantum mechanics course that you can take for free on Brilliant? My course will help you understand what a wave function is and what the difference is between superpositions and entanglement. It also covers interference, the uncertainty principle, and Bell's theorem. And after that, you can continue maybe with a course on quantum computing or differential equations. Brilliant offers courses on a large variety of topics in science, computer science, and mathematics. All their courses have interactive visualizations and come with follow-up questions. Whether you want to know more about large language models or algebra, want to learn coding in Python, or know how computer memory works, Brilliant has you covered. It's a fast and easy way to learn, and you can do it whenever and wherever you have the time. And they're adding new courses each month. And of course, I have a special offer for viewers of this channel. If you use my link brilliant.org/Sabine or scan the QR code, you'll get to try out everything Brilliant has to offer for a full 30 days. And you'll get 20% off the annual premium subscription. So go and check this out. Thanks for watching. See you tomorrow.